It's an enormous pleasure to welcome Professor Coralia Cartis from the Mathematical Institute at University of Oxford to speak to us today. We can also see collaborators on the screen there, and Lyndon Roberts from Sydney, of course, will be familiar to many of us. Yeah, Coralia is from Oxford, PhD from Cambridge. Can't complain about the pedigree there, Coralia. It's pretty top-notch professor of numerical optimization there, and has a whole bunch of fascinating research. I'm very much looking forward to hearing about today's topic of dimensionality reduction techniques for optimization problems. I'm wondering if it's using optimization to do the dimensionality reduction, but we'll get there. Very curious. But Coralia works in a whole bunch of nonlinear optimization and applications and everything from climate modeling, signal processing, machine learning, you name it. So it's with great pleasure that I hand over to you, Coralia.
Thank you very much, Professor Kate Smith-Miles. Thank you to the Optima team for the organization. This is a very special invitation. Indeed, I look forward to sharing with you a few strands of my work that I've tried to put together under this umbrella topic, and they are indeed connected. And indeed, a good part of it is with my former PhD student that you may know, Lyndon Roberts, who is now at Sydney, and also with former PhD student Zhen Shao and Adileto Temisov, postdoc Estelle Massar, and industry collaborators Jan Fiala from NAG and Yari Fox from RAL. So, in fact, my talk starts with a detour, because the techniques I will use, so here's the surprise, so I hope you will find this surprise, is to do with sketching. So I'm going to try to bring tools from randomized, from random matrix theory, from randomized numerical linear algebra, from stochastic geometry, to use for improving the scalability of optimization algorithms. So I will start with an introduction to some key ideas in these techniques. So sketching is a technique that tries to do the following. So assuming I have a vector x in Rn, and throughout this talk n will be my ambient dimension, and I will think of it as large. So I'm trying to take a given vector and project it into small dimensions, into a space Rm. So m will be considered as small compared to n. And I do this with a matrix S. And what I would like to do is, of course, we can project this in many ways, but I would like to do it in such a way to preserve the length, to approximately preserve the length of the projected, of the given vector when I project it. So in other words, I'm trying to satisfy a property of this form where the length of the projection is essentially distorted by plus minus epsilon s compared to its original length. In other words, I'm trying to preserve pairwise distances between points. That's another way of saying this. So the question is, what kind of matrices S have this property? There is the celebrated Johnson-Linden-Strauss lemma, some of you may be familiar with. It's really in the field of random matrix theory, a well-known result. So if S is a scaled Gaussian matrix, meaning it's a matrix where its entries are drawn independently from a normal distribution with mean 0 and variance scaled with respect to the dimension m, then and m is prescribed to depend on the accuracy that I want to obtain in my projection and the probability of its success. So what we have is that so such a matrix indeed satisfies such an embedding property, such a length preservation property. And this picture here on the left tries to illustrate this. So it's a simple plot for different vectors x. So I draw randomly different vector x just to have a So I'm trying to explain this result, so I can draw X randomly. So this S then acts as a sampler, and a rescaler, and I project this relative error here, and you can see that it concentrates around 1, which is very much what this result is saying, and it concentrates with high probability. To see that this is a high probability result, you could define this 1 minus delta as some delta plus, and then this log in the size of m will transform into a if we rescale the log here, log of delta s as some delta hat, then this 1 minus delta will become an exponential exponentially high probability. So high probability result. And another thing I want to say here is that if you look at this result, n was our large dimension, but n does not appear in the choice of m. So m does not depend on the ambient large dimension n, and it depends polynomially in the accuracy epsilon s. So we have epsilon s we can choose, and it also doesn't depend on n. So this the fact that it's free of it's independent of the ambient dimension, of the large dimension, is something that we can use for gaining scalability. Now, this result says something when you have when you're trying to project a vector, a given vector, or a finitely many given vectors. But what about if I'm trying to project a whole subspace, infinitely many vectors? So if I have a given matrix A that is of size n times d, then I'm trying to project and to preserve the length of the vectors in the column space of A. So then I have the subspace embedding properties. So I'm looking for a matrix S that preserves the length of AY approximatively. And again, scaled Gaussian matrices satisfy this property, but now I have to have a larger sketch size here. M is now proportional to D. So if I cannot go much below D, if I go below D, as this plot say, if I go below D, the relative error is large. But as soon as I'm proportional to D, just slightly over D is enough. Indeed, then this error gets of the projection gets very small. This, in fact, is the optimal result you can have in this subspace embedding. For subspace embedding qualities in terms of the size of the sketch. So you can project proportional to D or the rank of the matrix A if the rank is not, if the rank is smaller than D. The Gaussian is the ideal projector in that respect. That's how much reduction you can get when you project from the large N, when you project down, when you try to project the vectors in this subspace. So there is a catch here in that the ambient dimension does come in when you form S times A, because S, being a Gaussian matrix, is a dense matrix. So when you apply it to A, N, the ambient large dimension will come back in. So the natural question arises, are there other ensembles than Gaussian that don't have this dimension dependence coming in when you form the product S times A? Indeed, there are sparse choices for S, for the sketch matrix S. If I give you a matrix A and I tell you, reduce the large dimension of this matrix, the large dimension N of this matrix, then you would think, well, let me just pick uniformly at random columns of A. Such a sketch matrix S is still underdetermined, and it has one non-zero per row placed uniformly at random. So these are these uniformly sampling matrices, but we can see very easily that if A were to have one row that is much more important than the others, because, for example, then the magnitude of the entries there are much larger than the other rows, then I have a positive probability with such a sketch to miss that important row. So indeed, if I try to derive similar properties as for Gaussian matrices, where I preserve the length of vectors, this will not be true in general for a uniform sampling matrix as a choice of S. Indeed, people have derived such results for sampling matrices, some embedding properties for matrices, but you can see that the size of M in such results depends on D as D log D, so it's worse than D. But also we have here a term, mu squared, which is the coherence, the so-called notion of coherence of A, which measures the similarity of the rows of A. I don't need to define it here. There is a precise notion that looks at whether A has some rows that are much more important than others. If that's the case, then you need to sufficiently sample. You need to have an S that's sufficiently large to maintain such good embedding properties as Gaussian matrices had in preserving length of projected vectors. So these matrices, from an embedding point of view, have much worse properties than Gaussians. Are there other sparse ensembles that have good embedding properties better than sampling? The answer is yes, and these are the so-called count sketch matrices or hashing matrices. So a simple change from sampling that has one non-zero per row, hashing matrices have one or more non-zeros per column placed uniformly at random or with appropriate probabilities. So in that case, what you see is that because of the underdetermined nature of these matrices, they will have multiple non-zeros per row. And then when you apply them to A, they will start taking linear combinations of rows of A, which will mean that they will hit all entries in A, and then they will give you a better embedding. Still, there is some dependence on coherence, but it's different than for sampling. And in fact, we were able to show that with Zhenshao and Yan Fiala that we can recover for hashing matrices, and with one or more non-zeros per column, you can recover this optimal dimension dependence here of m proportional to D, provided the coherence is sufficiently small, but still we can have m proportional to D as for Gaussian matrices for this hashing, sparse hashing embeddings. So there are sparse ensembles, that's kind of the takeaway message here, that have good properties, good embedding properties, so that we don't have, so that we can use them more efficiently when we apply them to given data. Not so that we don't have such expensive products as with Gaussian matrices. So there we have a trade-off between the cost of applying these ensembles to the given data and also their quality of embedding properties. So now the question is, how can we use these ideas in optimization? So let me try to justify to you that in fact many of you may already be using them. In fact, these ideas have appeared frequently in supervised learning. So I will give a kind of a general umbrella description here for supervised learning that will try to capture different instances such as binary classification, deep neural networks, and regression problems, linear or nonlinear regression. So in all these instances, what we have is that we have some data that at least some of it is already labeled, so we know whether a patient has the disease or not. And what we are trying to do is to find a model that best describes this data as a continuous function of time and in some continuous way. So from a class of models that we select, we decide what the class of model is. We want to pick the best model such that on the given data that we have, the model output at the data points matches the labels we already have for that data. So how to formulate that mathematically? So the data is U and labels Y. The class of models is PU. And then we take, for example, a regression loss that measures the error between the model output at data points UI with their labels YI. So it measures it matches this in a mean squared error type of way. So then we form our so-called training loss objective to find the parameters X of our model PU such that this mean squared error on the training set is minimized. So we want to find this x such that the sum of functions takes a small value. So it can be also not, it doesn't have to be a regression loss. This L function here that measures the error between the simulated model output and the observations. It can be a logistic loss or other type of losses, but here I assume they are smooth or smoothed out. So we have a continuous differentiable function. So to say it succinctly, we have a sum of functions. Each term in the sum corresponds to a data point, the error at the data point. And we have, and there are many terms in this sum, many data points. We also have training parameters x that we want to find. And this number of parameters is also large. So if I think of, for example, the binary classification, the selection of model here, PU, is a linear hyperplane. I try to find the separating hyperplane, so it will be a linear model in the parameters x. For deep nets, this is a nonlinear, highly nonlinear model that takes the weights of the network as and the biases as the parameters, and then this the error at the data is going to be this convolution through the network where I compose the data and I use some kind of ReLU activation function. So linear compositions through the weight matrices of the initial data, and then I threshold that with, say, a ReLU function. For regression, of course, we have the L2 error here. Okay, so this is a deterministic formulation, but of course, underlying it, we have a stochastic problem, because what we would like is with this model PU, we would then like to use it to predict labels for unseen data. So that is how we can summarize these problems. And then where does sketching come in? Well, we can sketch in two ways. We can sketch in the observational domain. And I would like to justify to you that, in fact, anyone who has done a training of deep nets has, in fact, implicitly used sketching when they used stochastic gradient descent. So if I take my sum of functions, I'm going to now interpret stochastic gradient descent for you in this kind of sketching perspective. So I take this sum of functions, that's my training loss objective that I'm minimizing, and then I can uniformly at random, I subselect entries, I subselect functions fi, and I form a reduced objective that only takes a handful maybe of these terms fi, so the errors at each data point, so just a subset of the training data. And then I can take a gradient step for this. And we do this in machine learning because we cannot afford to calculate the whole gradient, the full batch gradient for our training loss function. So what we have to do is we have to subselect and just look at the subset of the data. But in fact, all we are doing when we are doing that is to consider this reduced objective that is nothing but if I take all my data points, f1 to fn, and I put them in a long vector, and I take sk to be a sampling matrix, so a uniform sampling matrix underdetermined, just as like I said before in the sketching descriptions, then applying such a sampling matrix to my data functions gives me exactly this reduced objective over the subselected entries fi. So in fact, what I'm doing is I'm sketching in the data to get a reduced objective, and then I'm taking a gradient step for it. That's exactly equivalent to stochastic. It's exactly the stochastic gradient descent. So when we apply stochastic gradient descent, we sketch in the data, but I thought with a uniform sampling matrix. Now, another way to sketch is to sketch in the parameters. So in the parameters, I can do a similar thing, but in a dual sense. I transpose my sketching matrix. My SK throughout this talk is an underdetermined matrix. So SKT is a tall matrix. So I can view my X, which lies in Rn, as when I project back a reduced vector Y that lies in Rm through my SK matrix transposed. So if SK is a sampling matrix, so uniform sampling matrix, then when I apply SK transpose to Y, is nothing but doing block coordinate methods. So this approach, when SK is a sampling matrix, will keep some of the entries in X fixed and will only optimize the entries corresponding to the non-zero entries in SK. So it is really a block coordinate method, nothing else, but random block coordinates because SK is chosen randomly. So a uniform sampling matrix SK gives us, when we sketch in the data, gives us a stochastic gradient descent. When we sketch in the variable in the parameter domain, gives us a block coordinate, random block coordinate method. But and these methods have convergence guarantees that are essentially typically with positive probability. So with positive probability, I can guarantee that the gradient of these methods gets small, or that in expectation, the gradient gets small. But that still means that with positive probability, I may fail. So can I get better algorithms than that? Why? Because I already tried to justify to you that from a random matrix theory perspective, SK uniform sampling as a choice of sketching matrix is just not a good sketch. So if I were to use better sketching matrices, like in the JL, that have good JL embedding properties, can I get a better algorithm? And the answer is yes, I can get almost sure convergence. So for the remainder of my talk, I will only talk about sketching in the parameter domain, so subspace methods. I leave out sketching in the data. It's a whole other story. So I will focus on variants of random block coordinate methods, in fact, of random subspace methods. We don't need to have blocks, but I will also talk about block methods. So I will sketch in the parameter domain first. And what I will try to do is to show you that sketching in the parameter domain can improve the scalability of optimization algorithms. It's a generic tool that can be applied in different optimization algorithms. And I will start talking about methods that are, in fact, quite scalable, derivative-based methods, and how can we improve further their scalability. And I will explain in what sense. And then I will get more and more to methods in optimization that do not scale very well, derivative-free and global optimization. And I will try to show you that these techniques can improve their scalability. So let us begin with derivative-based methods. So in derivative-based methods, so now I will abstract a bit. I don't need to think explicitly about sum of functions. I have a smooth objective f. And what I'm trying to do is, so I will first say that I can take any general optimization algorithm for this problem, and that I can view them in a very general way, so that I can encompass many algorithms. I'm speaking quite generically here. You can view methods for non-convex optimization. I don't have to have f being convex, as generating iterates xk that approximate my local minimizer, so a point with a zero gradient. So I'm trying to generate iterates that approximate such a local minimizer. And at every iteration of such a method, instead of minimizing my complicated function f, I approximate it by a simple local model, so that I calculate a step s by minimizing this local model that has here the function f at xk, its gradient at xk, and then maybe some second order curvature information bk. If bk is 0 and I minimize this, I get gradient descent. That's all I'm saying, that this encapsulates gradient descent methods, steepest descent methods. If bk is has some curvature information, then I get quasi-Newton. If it's the true Hessian, I get Newton-like methods. So this would be my typical first or second order optimization algorithm with some, then after I calculate such a step, I have to safeguard the step so that it's not too long, and I ensure I get decrease in F. So then I have to add some learning rate, some line search, or some trust region, or some regularization term to constrain the size of SK, of my step SK. Right, so this is my typical algorithm. So now what I do in random subspace methods, I say that instead of solving this model or even constructing it in the full space, I'm going to construct it in the random subspace. So at every iterate xk, I draw a random subspace sk, and I replace my my search direction. Instead of it being in the ambient dimension Rn, I calculate it in the reduced Rm space. So I replace S in this model by this projection, Sk transpose S hat. And when I do that in the model and using properties of inner products and transpositions, I get this reduced model. So in my reduced model that I will now use to calculate the step, I have here the projected gradient, and here I have a projected curvature matrix if it's present. So this is my reduced model. So the first plus of this is that I only have to calculate a direction in a reduced space Rm, which is good because it will be cheaper from a computational cost point of view. But I want you to notice another difference. I only need projected gradient and projected Hessian. In other words, this projected Hessian, this projected gradient here tells me that I do not actually, in the algorithm, need to see the full gradient. I only need to see its projection. So for example, if SK was a sampling matrix and I calculate my gradient by finite differencing, I'm only requiring that I calculate a subset of the finite differences. So if each finite difference, for example, was calculated on a different processor, I only need to have back, a couple of finite differences, and I can proceed with my algorithm. Similarly, I can view my my curvature. If I construct the gradient by automatic differentiation, then I only need an inner product with the gradient that can be calculated from the tangent linearizations that we need to form in AD, but I don't need to actually compute the full adjoint here and store it and so on. So I don't need to see full problem information ever in these algorithms, and I calculate cheaper directions. Here I put, and then I do the usual mechanism. This stays absolutely unchanged. I do a line search, or I do a trust region or regularization, and I calculate, I safeguard this direction that I now project back into the full space, that the next iteration I draw another subspace. So under what conditions can I ensure convergence of my algorithm? If my projection matrix is bounded, and if with a certain probability I capture correctly the length of the projected gradient, that's all I need, okay? And this epsilon s here can be a half, can be anything. It doesn't have to be small. Then I can guarantee that this variance of trust region or line search or regularization, these random subspace methods, are almost surely convergent. And in fact, I can even get their global rate of convergence for driving the true gradient below epsilon, which I never need to see in the algorithm, but I can guarantee it in theory, that the true gradient will go below a small epsilon in epsilon to -2 iterations. Epsilon to -2 iterations, it's exactly the complexity of the full dimensional methods without subspaces. This complexity changes by a constant multiple here, which depends on the success probability of this less preservation of the gradient. But now I'm trying to tie things together with the sketching. This property here is nothing but one side of the Johnson-Lindner-Strauss lemma. So in fact, SK here, what SK matrices will have this property? Any SK that embeds correctly one-dimensional vectors will have this property. And Johnson-Lindner-Strauss immediately gives me this property, and it tells me what the size of S should be. So here we are. This property is in fact very weak, and it will be satisfied by scale Gaussian matrices with essentially arbitrarily small choice of M. So the projection, the subspaces that I can choose in my algorithm can be very small. They do not depend on the ambient dimension or anything else, because here it's not even a matrix, it's just a vector. I can also have sparse matrices like hashing matrices, provided they have sufficient non-zeros per column then I don't have any coherence requirement here, and I also can have small subspaces. Now, for block coordinate methods, this is not so simple because these matrices, the sampling matrices, do not have this JL property so straightforwardly. For them, I need to require that the gradient has similarly important entries. If that's the case, block coordinate methods will have almost short convergence. Otherwise, this theory can only guarantee for me convergence in expectation. Okay, now let's try to, I won't give you more details about the theory because time is short about where do this comes from. But basically, I do want to emphasize the one aspect that in these algorithms, in some iterations, my embedding property will fail, but it doesn't matter. I can have this noise in my algorithm, this bias, it's fine. I can keep going, and I will still be okay from a convergence point of view. We use here probabilistic model theory to prove a convergence, but we have much weaker assumptions. So I want to illustrate a little bit this framework on random subspace Gauss-Newton methods. So for nonlinear regression problems. So in nonlinear regression problems, so F now has a special form. So it's a sum of functions where each term is a mean square loss here, regression loss. So I have the regression loss, and Gauss-Newton linearizes these models at every iteration and solve a linear least squares. So now what I can do with these sketching matrices, with random subspace matrices, is to actually only sketch my Jacobian matrix. So I only sketch the matrix of first derivatives of these error terms here. And in other words, for example, if SK was sampling, I would only calculate columns of my Jacobian. And in fact, I've used this approach in some climate modeling applications, because there, to calculate the Jacobian, I need to do finite differences. So I need to run the climate model for every finite difference separately. I can do it in parallel, but it's still a lot of computational effort, especially if I have a high resolution model. So then I prefer to just do a few of them, and that's exactly what we can do here with these models. So or you can have other problems. I have a numerical illustration here that's on a nice problem where these methods work really well. I'm doing logistic regression for a chemotherapy classification problem. So that's the patient binary classification. Does the patient have or doesn't have the disease? So let me illustrate to you how even just block coordinate Gauss-Newton method works here. So I'm still using blocks numerically, even not the best sketching matrix. But this is the typical performance that you will see either all the way or at least in early iterations of these methods. So I have here in the first plot on the horizontal axis iterations of my full Gauss-Newton method, where I see full problem information, and then my and then block method. So I only calculate columns of my Jacobian, a subset of the columns. So, and then on the vertical axis, I have the objective decrease of my regression loss. So in purple is the full dimensional method, and you see that it takes very few iterations, while the block methods, the block Gauss-Newton methods take much more iterations. But when we go to runtime, we see that the Gauss-Newton method takes a lot longer, while the block variants take much less time. And similarly, in the bottom plot, I look at how much problem information have I used in terms of gradients or, Jacobian columns. How many Jacobian columns have I calculated to obtain my iterates? And again, you can see that the block methods save and are much, much better than the full dimensional problems. So iterations is not really a good measure for these methods, or it's not telling the whole story, because these methods do give us gains in exactly what we want to gain: runtime for large-scale problems, runtime and use of problem information. We don't need to see all the problem information. We don't need to store it, and indeed we can progress without it. Now let me move on to the next class of algorithms that Lyndon Roberts and I really wanted to gain some scalability for. And this is the so-called model-based trust region methods. This is derivative-free. And I will give you a gist of what these methods are trying to do. So they are state of the art for this subset of optimization methods called derivative free, where what you assume is that you only have function values. They may even be corrupted by noise. They may be stochastic. You do not have derivative information about the problem. The function may be smooth, but you just don't know its derivatives. And you're not even trying to approximate the derivative in the run of the algorithm. That's not your aim. So what these methods do is they still fit into this earlier framework of you approximate the complicated function by a simple local model. But now the local model here has f at xk like before, but now both this term gk and this term are not the here is not the gradient, and here is some approximated Hessian. So the most important thing here is that here gk is not the true gradient. So this is for the full dimensional model. I haven't told you about subspaces yet. So in this model-based trust region, really state-of-the-art for DFO, we calculate this GK by interpolation of function values on a chosen interpolation set. Now, to construct even linear models here, you need, because you have to construct this vector GK, you need n+1 evaluations. And not to mention, if you have to construct HK, you have you need even more points. Okay, so because you have to then solve to construct a linear system to construct this model, you have a computational linear algebra cost of n to the cube to n to the 6 per iteration. Now, the evaluation cost is not as bad as it seems, because though you have to evaluate f at all these interpolation points, after the initial evaluations, on each iteration of these very clever algorithms pioneered by Mike Powell, these models just update this interpolation set. So these methods are designed for expensive objective evaluations. So you do want to, after the initial evaluations, to just have a handful of evaluations of f per iteration, because f could be the result of simulations, like I was talking about Kleinman models earlier. But the computational linear algebra cost is very bad, and really prevented these methods from being applied to large-scale problems. So random subspace methods or subspace methods for these class of problems seems an ideal choice to try. So what we did is we said, okay, fine, choose a random subspace and just construct this interpolated model in a subspace M of very small dimensions. So, and then you only have linear algebra costs that are linear in the ambient dimension N. So, and then the choice of the subspace is also small dimensional. So this helps us because we then also have less interpolation points that we need. We only need to work in RM. So we save in evaluations and we save especially in these linear algebra costs. So what do we see numerically? Indeed, this is a sort of performance profile accumulated a CDF of a density of so we are trying to measure percentage of problem within our solver was so okay, let me tell it more simply. Sorry. So this kind of performance profiles, they show you within how many essentially gradient evaluations, but here we just mean number of evaluations of the function times the problem dimension within this many, so four times problem dimension, so 4 times n gradients, what percentage of problems were solved by a given solver. And what you see here is that the subspace variants are competitive with the full solvers, which are in black here. So they are competitive with that. And the main thing that you can see in the table is that, in fact, if you give a time budget, if you have a budget for your problems, and we are solving here 1,000-dimensional problems, which is much larger than we could solve without random subspaces. So with the full dimensional solver in a 12-hour time budget times out 93% of the time. But our subspace variants time out much less. So this is exactly the remit that's very good for these classes of problems. You want to make fast progress, you only have a limited number of time or data available. And similar to what I showed earlier, these objective decrease plots, you can see that these random subspace variants here are much faster, make much progress than the full dimensional variants here and here that haven't yet moved on these problems. Okay, so I don't want to extend much more. Can I go on for another 5 minutes or?
Yeah, please do.
Okay. So now I want to go to the hardest problems, the global optimization, NP hard problems, as Professor Smith-Miles knows very well. These are very challenging problems. And in fact, their scalability is really, really difficult, especially if I'm trying to solve generic problems. This is very much, in some sense, my remit. I'm trying to just have generic solvers for non-convex problems and black box. So can I apply these random subspace ideas here? Indeed, I will try to carry through a very similar, very, very similar framework to before. But now, instead of constructing a local model in each subspace, I will just take my projected function in that subspace and try to optimize it globally in the subspace. But then I have higher hopes. Can I then hope to get the global minima overall, or an approximation of it, of course? So let me summarize. At every major iteration K, so I have these random embeddings for global optimization. At every major iteration K, I draw a random sketching matrix, here only Gaussian. And I draw it at an anchor point pk, which I can think of as the best point I found so far in terms of the point with the smallest function f, value f. So at that anchor point, I draw my random subspace, which was the same as before, really. And at this point, so pk is, I can view it as xk, and then I just minimize my function with any solver in that subspace. And this can be in the whole of Rn if I don't have any constraints, or it can be with linear constraints in a box. If I have an original box domain, then I can carry over the box constraints here. And then I find some other point, yk, and then I form xk plus 1 to be the best point I found in my subspace. And I assume that in this subspace, I can use any global solver that I want, provided it can guarantee to find me, at least with some probability, an approximation of the global minimizer in this subspace. And the idea is that global solvers are good and efficient if I apply them in small dimensions. Okay, so I only solve here a small dimensional problem with any choice of solver. This framework is almost surely convergent. I will enter an epsilon neighborhood of a global minimizer with probability 1 for Lipschitz continuous functions f. And provided this, we can prove this provided that the global minimizer is attained at some point x star. This proof goes beyond sketching techniques, beyond Johnson-Lindstrauss lemma. We really needed to use stochastic geometry here. But, and with stochastic geometry, I really don't have time for this, sorry. I quantify some probability of intersection of a random subspace with a ball, and that's where we use stochastic geometry tools. We can quantify this probability of success fully having a random subspace that intersects a ball of a global minimizer in a general case of Lipschitz continuous functions. And this probability of success depends, though, exponentially in the ambient dimension, which is not surprising because I have a general objective, and this problem is NP hard. However, this probability of success, we can provably show it's better than for random search or uniform sampling, as it should be, because we are working in a larger subspace at every iteration, and we use a global solver in each. But when are these random subspace methods particularly useful? When can we actually get proper scalability for global optimization with random embeddings? When we have a certain special structure. This special structure is called low rank or low effective dimensionality. So here's a picture of such a function. This sinusoidal curve, from an optimization point of view, this sinusoidal surface, from an optimization point of view, interesting things happen only in this direction. In the complement subspace, the function is constant. So from an optimization point of view, if I knew this subspace of variation, I could just solve in that subspace, and it would be very easy, because we assume here this subspace is small dimensional. Such a structure occurs frequently in overparameterized systems, or at least approximatively in overparameterized models and systems. Because when you have an overparameterized model, your model will not change when you change some of the parameters, because you have too many parameters. So it's going to be invariant to some of these changes. As long as these changes are linear, you get this kind of structure, or at least approximately linear, so that you can get this structure at least approximatively. So in this case, if we do not have constraints in the problem, when you have one global minimizer, you have a whole subspace of global minimizers. So if you were to, of course, if you know this subspace a priori, the problem is trivial. But in this context, we assume we do not know the subspace a priori. If we know its dimension, dE, its low dimension, its low rank, then one random subspace draw, if we draw one random subspace of the appropriate dimension, low effective dimension, it will almost surely, with probability 1, intersect the random subspace. It will intersect a subspace of global minimizers. That means that in my random subspace framework, I only draw one random embedding. I solve in that random subspace, and I will find my global minimizer. And this is irrespective of how large my ambient dimension is. These bounds here are independent of ambient dimension. If I do not know dE, then I can start drawing a subspace of 2 dimensions, then I grow to 3, and so on. And then I will, even if I don't know dE, I will reach dE without knowing it, and I will just notice that my function stops changing. Indeed, so with at most dE random embeddings, I will find my global minimizer. And what I want to show you is some numerics here. So I took Baron, which is a state-of-the-art solver. And I applied, I took a standard test set of global optimization problems. And I constructed, from them, I added fake dimensions and zeros, basically. And then I rotated these zeros so that the effective subspace is not aligned with the coordinate axis. And in this way, I can get synthetic examples where I know the effective dimension, and I know for sure that these problems have effective dimension, but I don't know the subspace. So I draw here in this picture subspaces, I assume I know dE, and I apply Baron to this test set with random embeddings, with one random embedding, and Baron without random embeddings. So from a success probability, I see that Baron, and then I increase the ambient dimensions. The N is big D, and it grows from 10, 100, 1,000. And what you notice is that the Baron, as the ambient dimension increases without random embedding, its success of finding and guaranteeing to find a true global minima decreases, while the success of the random embedding framework essentially stays unchanged, as the theory predicts. This is just finding local solutions, and this is CPU time. We can then take multi-start nitro. Nitro is a local solver, so it's a bit not the right thing here, but it has a multi-start procedure. So for success probability, because of the multi-start, because the number of starting points, it doesn't really scale with the ambient dimension. This stays unchanged for the unembedded solver. But when you look at function evaluations, they grow compared to our embedded framework, and similar for CPU. So you can see this numerically quite easily, and honestly, without much effort, because the framework is very simple. I won't talk about constraints. So let me finish by connecting to, as I started, with machine learning and supervised learning. This idea of random embeddings, in fact, was attempted for improving the scalability of Bayesian optimization. There is this, I would say, quite famous paper, Bayesian optimization, a billion dimensions via random embeddings, where this random embeddings framework was applied inside the Bayesian optimization algorithm. When we saw this paper, it wasn't clear to us whether, well, we thought that these two things are disconnected, and that we could try to use this with any other global solver. And indeed, that is possible. And we also gave much more theory than in this paper. There are several papers in machine learning that actually essentially conjecture that the training landscape and show numerically that the training landscape is a landscape with low effective dimensionality, that only some of the parameters are important. And of course, we don't know which ones they are a priori. In fact, there are papers that randomly projected the subspace of training parameters and show that it's sufficient to train a subset of the parameters, and you get a good accuracy and even if you just do that. So this seems to indicate that indeed there is some low rankness present in these nonlinear training landscapes. And there are more and more works on this. There are some very recent works by Rebecca Willett, Misha Belkin, that look at low rank for deep nets, but not even in the parameters, in the data. So they show that, especially Willett shows that for linear layers, the trained network is actually low rank in the data. So if you look at your network as a function of the data, then it is actually a low rank function. So then what our more abstract frameworks try to justify that these approaches are viable and suitable in these tries to make sense why these random subspace or projection methods work in this context. So here are some references, and thank you very much for your attention.
Thank you, Coralia. What a wonderful talk.